Our team is Hearing with the Eyes, assisting the hearing impaired during the COVID-19 era. I'm on the right screen here. So first we'll introduce ourselves, then we'll dive into some motivation and project selection information and some background information on our project. Then we'll take a look at some of the design requirements and specifications and the description of our project, as well as some related theory to it. And then we'll talk about some key design descriptions and specifications. We'll talk a bit about testing results and the schedule, cost analysis, and then we'll wrap things up with some future work, some code standards and constraints, as well as ethical issues. And then we'll take questions. My name is Wyatt Madej. I am the team leader and the software lead, and I have expertise in coding and project management.
My name is Kevin Zhang. I'm part of the software team. My expertise is in software development.
Hi, my name is Kieran Clifford. I'm the hardware lead, and I have an expertise in electronics and hardware management.
I'm William Barker. I'm part of the hardware team, and I have an expertise in electronics and power systems.
So our project was motivated really by the fact, as why a lot of other projects have been today, and will continue to be motivated by later in the day, by the fact that we are living in a pandemic. And then the fact of the matter is that with relation to our project is that the hearing impaired often rely on facial expressions and mouth movements when communicating with hearing persons. It plays a really, really big role in the communication between the hearing and the hearing impaired. And this part of their communication has become really difficult because of masks during COVID-19. And masks may be here for longer than we hope for and anticipate. Other solutions exist to this problem besides ours. However, they tend to cost too much, are not widely available, or they don't completely solve the problem. We found two big examples of this, one of them being the Donut Robotics C-Face, which is a product very similar to ours. However, it's constrained by the fact that it isn't actually in production yet. It is really only available as a Kickstarter campaign in Japan. It's also a bit more expensive than ours, and it's very bulky, and it's not exactly super comfortable to wear. There's also Google Live Transcribe, which is an app-based solution, but it doesn't really solve the problem of social distancing.
So as you can see here, our main goal was to create an effective speech-to-text solution for the hearing impaired with the criteria of being easy to use, portable, cost-effective, and having reliable speech-to-text. So the three alternatives that we considered were an app-based speech-to-text service contained within 2 phones, which is prohibitively expensive, but it is easy to use. A hardware-based approach where you have a permanently installed screen and microphone, which is relatively easy to use, and you have reliable speech to text. But we chose the third alternative, which is to use a mask that connects to a mobile device in order to do speech to text. And as you can see here, we weighted cost effectiveness and ease of use very highly.
So in summary to this part of our presentation, we want to design and implement a low-cost mask and app to aid hearing impaired people during the COVID-19 pandemic. It'll be used during this pandemic and possibly elsewhere, and especially with an emphasis in environments where masks must be worn, classrooms, for example, or retail spaces.
So this is our design system requirements that we created initially when we first started this project and still continue to pursue as we are developing our software and hardware. This being accurate speech transcription, low cost, reliability, and accessibility. So, so this is our need specification objective tree in which we break down our 3 system requirements: accurate translation, reliability, and accessibility, low cost falling under accessibility. So these are our 3 marketing requirements in which number 1, like the product should be able to translate speech text with a high degree of accuracy. Number 2, it should be easy to wear, ensuring that it's not uncomfortable or unwieldy. And number 3, that the product should be highly accessible to all users, regardless of who the user is. And here's our marketing / engineering requirements table in which we combine both our marketing and engineering requirements along with our justifications for them. And like this is like sort of a marketing engineering trade-off matrix in which you are able to visually see how our system requirements match up with the broken down requirements, which, as you can see, like accurate translations having a strong negative correlation with comfortability and how easy the setup is. For reliability, a strong negative correlation with error-free speech-to-text, cost, and ease in setting it up. For accessibility, having a negative correlation with all of the categories besides ease of use and cost. And finally, cost, which has a strong negative correlation with ease of setup and comfortability.
For the overall build of our mask, we're looking for just a mask that is assisting with the hearing impaired, utilizing the Arduino Nano that has a Wi-Fi and Bluetooth chip enabled to connect to the user's device and accurately transcribe the speech through the software on the Arduino. This is just an overall image to look at so you can see how the basic setup of how the system will work.
So before we dive into some of the nitty-gritty about everything, we'll just provide some background related theory, mostly focusing on how this translation works and transcription works. We are utilizing the Google speech-to-text API. This works, it is cloud-based, and Google is utilizing neural nets to do this. And it does so by using what they call memory cells. And what they do is they remember data and connections that the neural net is trained on. And this way they're able to transcribe speech into text with a really, really high degree of accuracy. And the chart below kind of gives that background and how the theory on how Google is doing that, where they're taking data in and transcribing it via their speech-to-text API and their auto machine learning natural language, and using all the data that they've collected and transcribing that back into text.
So in general, for the behavior module, the inputs are audio, which is sent from the discrete microphone to the audio processing unit, and the algorithm that we're using, which is the Google API that we're using to convert the speech to text. And the output is translated speech into text, where the incoming audio is translated and displayed on the user's device. And the data flow diagram is on the next slide. So you can see here, the input speech goes into the Nano, it's sent to the algorithm. The text output of the algorithm is sent back to the user's device via Bluetooth Low Energy, and the user's device receives the signal and displays the text in the designated app.
Functional breakdown of our project. We plan on having a small battery. Right now we're using 3 AAAs, but plan on trying to go to a capacitive switch that also inputs the microphone that will be connected to the mask and out to the phone. For a more in-depth detail, we'll have the microcontroller Arduino run the speech-to-text talk software and process the audio that it's receiving and send it out to the user's device. Just as fluid as we can get it and as small as we can make the mask is the overall objective of this.
So here we have our preliminary schematic and breadboard, and you can see the microphone, status LED, and switch all working. And on the next slide, we have the circuit that we built, and it worked, and yeah, it worked.
So here is our current app user interface, as you can see, in which we have a listen button, like a button to connect the Bluetooth device, 2 text fields, one being transcribed text, which is where we would put the transcribed text we get from the algorithm, and like the disconnected like indicates whether or not a Bluetooth device is currently connected.
Here's our demonstration video. So you can see that we have all the hardware set up on the left, and then on the right we have our phone. One thing we did run into during our testing that was a little bit that we didn't anticipate is that we developed the app in Android Studio, but the emulator that is built into Android Studio, you can't really test Bluetooth out with. So we did end up deploying onto a real device. That did work. You can see here the flashing red light shows that it is connecting and going into Bluetooth terminal here and selecting that device there, and you'll see the light turn solid red, which means it is now connected. And just launching our app, and that is what our app looks like on a phone, and hit the listening button, and which would then in the future start triggering the speech to text algorithm, and that would start transcribing the text there.
So on the software side, in order to test our application, like we use the Android device emulator in our app development environment, Android Studio. With this emulator, we made sure that the application was able to launch with no issue and ensure that the Bluetooth settings were launchable from the app to allow the user to connect the Bluetooth device if they haven't already.
For the hardware side, we set it up so that the Arduino was able to send and receive the data that's necessary through Bluetooth. And we were working on testing out the microphone for the connection to the Arduino, and just guaranteeing that the speech will transfer through the Bluetooth and everything set up fundamentally for the future.
This is our step-by-step test table here. So we did 4 steps in our testing. They all passed, showing that we testing our power button and our startup behavior, being that the status LED turns on, which displays that this system is on to the user, as well as others. Then opening up the application on the target device, which you saw in a few slides ago in the demonstration video. It does open up in an actual physical device, not just an emulator. Then we tested connection to Bluetooth after that, once we were able to open the application, and which we were able to connect the Arduino to our phone. And then just testing that the buttons within the app are working correctly. And as a result, everything is working as expected, and we were able to pass this part of the test. So we had 3 go, no-go milestones for our project this semester. The first one being to have an app structure and design created, and that is done. We wanted to have the Arduino Bluetooth connection all set up, coded, and ready to go, which was done, as well as starting the design and construct the wearable device hardware, which was also done. Based on these milestones, we were able to determine that our project is viable, and we will be on track for completion by the end of Capstone 2 next semester.
So in terms of cost, like we saw at the beginning of the presentation, we're trying to keep it as low as possible to keep the device accessible to anybody who may need it. So we're using an Arduino Nano 33, which is about $20 and is the most expensive part on the list. And everything else is sub $3, coming out to under $30, which we feel is a very accessible price point to anybody who may need this device for accessibility purposes. And the main code and standard that we're working with is Bluetooth IEEE 802.15, which allows the connection of up to 7 devices. And unlike a Wi-Fi solution, it allows for a minimal configuration, like a button press, which helps with accessibility. And Bluetooth Low Energy helps for a similar communication range and features of other standards while reducing power consumption. And in general, it won't be a limiting factor in our product.
Large ethical, so just take a look at the ethical issues. The first major ethical issue is asking the question of where does the data go? We have to ask this question because we are using the Google speech-to-text API. It is cloud-based. It is using and leveraging neural nets, which means that Google is collecting the data that we are inputting into their API. So from an ethical standpoint, we do have to ask, where does that data go? What's Google doing with it? How are they storing it? And if a user wants to know what Google has, how can we give that to them? And then second of all, prioritizing cost. Cost is a huge priority for this product and our project. We are, like we said a lot of times, our aim is to make this as low cost and accessible as possible to anyone and everyone who may need it. And so this raises the question of, if we do make it really accessible and cheap, what human cost do we run into there, if while sourcing parts, or if this project were to grow larger than just a capstone project. And then second of all, just prioritizing what components get what cost attention in terms of quality of the device itself.
So in the future for the software team, we plan to implement the speech-to-text algorithm and improve the user experience and interface to further improve our ease of setup. One issue we are experiencing but will resolve in the future is scaling the app for different devices, as some devices may have larger or smaller screen sizes.
On the hardware side, for the next semester, we're looking at getting it more streamlined with the Bluetooth low energy. Once we are able to get the Nano chipset in, sold out for most of the first semester. And the main focus on improvement is to make it smaller and have a lighter power source that's rechargeable, so that it can have more longevity, more wearability, and just more accessibility. One of the issues we ran into is getting the microphone to connect up with the Arduino, which we'll also be looking at trying to solve throughout the second semester.
That concludes our part of the presentation, and at this point, we'll take any questions.
Thanks, Mike, Kevin, William, and Sharon for your presentation. So, do we have any questions from the audience?